This is AQA GCSE Chemistry. This is the bonding topic and it fits within the dual award and triple award content. We're on bonding part 7. In this video, we're going to take a look at giant covalent substances. As always, we're going to recommend that you pause, have a go at each activity before reviewing your answers. So, within this video, we're going to look at the general properties of giant covalent substances, and we're going to look more specifically at diamond and graphite. So, let's start off with these first questions, identifying each of the three substances we can see. And two of these I've already mentioned in the objectives. You have got to be able to recognise them, and you may need to be able to show simple representations of them diagrammatically. But the first one, graphite, recognisable by the hexagonal planar structure that's held together by weak intermolecular forces because of the delocalised electrons that are present. On the middle, we have got silicon dioxide. Silicon dioxide is sand, so we've got silicon and oxygen combined together. But diamond is the familiar shape. Silicon dioxide has a lot in common with that shape. And we can see that each carbon is bonded to 4 other carbons. That's going to be really important as we go forward. A few questions for you to think about here. So why would we refer to them as giant covalent substances? And it is a giant lattice. There are lots of atoms. In diamond, in graphite, there are a huge number of carbon atoms in there. In 12 grams of carbon, there are 6 by 10 to the power of 23 atoms of carbon. That gives you an idea of the scale. And between those are covalent bonds. So there are lots of covalent bonds, and those covalent bonds are strong. So it's being held together in this giant lattice, hence giant covalent. Let's compare that to simple covalent, where we have water as an example. 1 oxygen, 2 hydrogens, that's your molecule. And then from there, we have got an intermolecular force to another molecule. Okay, what element are diamond and graphite made from? We've already discussed this. It is carbon. In diamond, each carbon is bonded to 4 other carbons. And in graphite, each carbon is bonded to 3 other carbons. So now let's have a think about melting points. And what we're looking for here, if you think diamond, if you think graphite, they don't melt easily. They require a huge amount of energy. So they have high melting points. Why? Well, I'm going to break this down into the key words for this answer. There are lots of something. And we've already spoken about what this is, but I'm going to build it up slowly. Whatever there are lots of, they are strong. So if we break that down, there are lots of strong covalent bonds. And that forms the first part of our answer. If there are lots of these covalent bonds and they are strong, lots of energy is needed to overcome them. You'll see parallels here with ionic compounds where there are lots of strong electrostatic forces between oppositely charged ions, therefore lots of energy needed to overcome them. In metals, there are lots of strong electrostatic forces between positive ions and delocalised electrons, therefore lots of energy needed to overcome them. The key here is to use the right words and the right terminology for the right bonding type. Any errors become a chemical error and you will definitely lose marks. So, of diamond and graphite, which will have the higher melting point? It's diamond. And it goes back to a question that came up earlier in the video. Each carbon is bonded to 4 other carbons. That means we've got 4 covalent bonds per carbon. Whereas in graphite, there's only 3 bonds per carbon. That's still a lot. The melting point is high, but diamond will be higher. On to the next question, and this is thinking about what happens to that 4th electron within graphite. And the 4th electron is delocalised. This mirrors what we discuss in metals. All metals, outer electrons are delocalised. In graphite, the 4th electron on each carbon is delocalised, which means it can move freely through the graphite structure. So, giant covalent compounds generally cannot conduct electricity. Why? It's because there are no free electrons to carry charge through the structure. However, graphite is the anomaly. It's the exception to that rule. And that's because there are delocalized electrons and they can carry charge through the structure. So then we've got a little bit more here about the properties of graphite. Why is graphite slippery? And give an example of where we use those properties. And graphite is slippery because of the weak intermolecular forces, which are caused by the delocalized electrons. That's what's holding the layers together. But it means the layers within graphite can slide over each other. They can easily break away from each other. And where might we see that? Well, the prime example, we talk about lead in a pencil, whereas actually it's graphite within a pencil. And when you rub your pencil across a piece of paper, layers are left behind because they can be broken off so easily. Graphite can also be used as a lubricant. It can be used to get door locks that have been blocked up, for example, so keys can move within there. Now, you do need, and I keep emphasizing this within this topic, you need to use the right terminology in the right place if you're going to be successful in the bonding topic. That takes us to the end of this video. Thank you for listening and goodbye.